Hello, I'm Quentin Marmire. I'm a lead technical artist for the special project at Epic Game. And today we are going to present with Robert Osborne and Julien Marchand how to generate a world for the Matrix Awakens experience.
The procedural city generation. So let's look together on how we have created a fully procedural city generator. Using very few simple inputs like basic splines, we have created a tool that could generate on the fly an American-like city. We will describe how we have used Houdini and Unreal to shape and art-direct it to our needs, and how we have used point clouds and the neural processor pipeline to generate it on a daily basis. This is a living autonomous city, 4 by 5 kilometers wide, with 260 kilometers of streets and 512 kilometers of furnished sidewalks, more than 7,000 unique buildings, 18,000 traffic vehicles, and 35,000 pedestrians aware of each other and respecting traffic rules. We will go over the step-by-step process that were required to make this work and what were the constraints we have faced. How it generates quickly a virtual world made out of 8 million nanite instances that provides incredible amount of detail from the smallest piece of trash on the ground to the nuts and bolts at the top of a building. And how we ended up regenerating that city 53 times to refine its procedural rules over and over and become what you can explore today in the Matrix Awakens experience. We've tried to use the full potential of Nanite, Lumen, Open World with Unreal Engine 5 to offer the most detailed virtual experience we could. But first, let's introduce one of the main tools we have used in the creation of our city, Houdini from Side Effects.
Hello, my name is Mai Ao. I'm the lead technical artist on the Side Effects Labs team. First off, I would like to thank Epic Games for the pleasure of doing this presentation together. I would also like to thank and acknowledge my former colleague Paul Ambrosiuson and my colleague Damien Panud, who have contributed greatly to this collaboration on the Side Effects side. Side Effects is a developer of Houdini, a high-end, comprehensive 3D solutions platform with a procedural node-based architecture. With more than 25 years of history, Houdini is widely recognized in the VFX industry with more than one Academy, scientific, and technical awards. You can think of a Houdini pipeline like a factory. Nodes are like machines that perform specific tasks. The machines can be chained together to form sophisticated networks like industrial assembly lines. The designs of these assembly lines are entirely up to you. Finally, the pipelines can be streamlined and organized into factories, aka HDAs. So all the controls you care about are exposed, and the rest is fully automated. What makes Houdini special is you can go from easy to understand low-level tools to a complex high-level factory that when looked from the outside does some sort of magic. The core purpose of a procedural pipeline is to serve the artists, to give them more creative controls and fewer headaches when they need to redo work. More importantly, a procedural pipeline is also scalable. You can often accomplish more with fewer people, as developers' time is valuable. The architecture of Houdini makes it possible to integrate the software's compute power deep into the pipeline. A pipeline is about a lot more than making 3D models. With Houdini, a lot of the user stories that can be encapsulated as tasks can be then translated into tools. These tools are developed with close collaboration between teams. Decisions are made together to address different departments' concerns, such as what should be on the UI and how should the data be transferred. When it comes to engine deployment, the tools are typically packaged as HDAs, which you can use in Editor through Houdini Engine plugin. With Houdini Engine's now free commercial licenses for Unreal, a larger team of artists and level designers can directly interact with Houdini tools maintained by a smaller team of tool developers. In a nutshell, once the tools are created and deployed to Unreal, the Houdini Engine plugin will power these tools inside the editor by talking to the Houdini library in the background, on your machine or on farm machines. As a real-time developer, when you need to start building your own procedural tools, Side Effects Labs is here to help. We're a small team, but we create a large collection of free and open-source Houdini tools, especially focused on real-time pipelines, as well as the quality of life of developers. You can think of Side Effects Labs as a public extension of your own R&D team, because the tools we make are based on the feedback of the community, and we make them so that they can be shared with everyone in the community. With more than 200 tools and growing, it is not unlikely that when you need to accomplish something, we may have a standardized tool for that. Labs tools span everything from modeling, photogrammetry, UVs, texture generation, asset export, third-party integrations, and more. We also ship a set of labs on Real plugin, which contains script and shaders that works with Houdini assets, or just generic all-purpose utility shaders. You can discover all this by downloading SideFX Labs' latest daily builds.
Thank you so much, Maya, for this overview of Houdini. And now let's have a look to the Matrix Awakens procedural city and how we have done it. As a starting point, we knew the Matrix Awakens would have to be an open world, a city that would be fully detailed and very large at the same time. We established that a 4 to 5 kilometer wide city would provide the ideal playground for the experience that we had in mind. We knew this environment would be the base for a lot of departments to work on and that they would need to be provided with updated data as we are modifying it. This had to be automated. We also knew that it would have to be procedurally generated because of the relative small size of our environment team versus the sheer size and level of detail we were aiming for. All of this was also considering that we would use Nanite technology. Nanite has changed the game. Because it removed all polygon limit and the resolution at which we can have details, now that 1 meter square can have up to 1 million triangles without worrying about performances, a city of 16 kilometer squares would have 16 trillion triangles. This brings a new problem. The size and the amount of assets on disk becomes a limiting factor. Also, bigger assets means slower iteration and less flexibility. We can't just brute force our way through. We have to find a smart way to slice the world. Early on, we were considering the use of OpenStreetMap. But unfortunately, the data it provides is arbitrary, unique in size and shape for any given place. That is too much work to translate and adapt, and that creates too many unique assets. Same would go for the natural follow-up of OpenStreetMap, creating a mega mesh of the city. But for the amount of detail we were after, that wasn't a viable solution. What we need to do is quantify the world and make our own construction set to build it. We would then rely as much as possible on instancing. Our work becomes then how to slice and dice a realistic world and replicate it the most precisely possible with those bricks. This is especially complex because in the real world, you will always find a piece that is almost impossible to reproduce with your bricks. That is where having full control over the geometry of the city becomes so important. We wanted to keep a tight grip on how much of the arbitrariness we would allow. First, we would start with a specific tool designed to create the base of our city, the city layout tool, or how to procedurally generate an American city pattern. It would only require two main inputs to start, a basic shape and the path of the main arteries. With few attributes and options available to adjust the road network setup, it would give you an American city layout. The rest is figured out by the tool. With only few spline inputs, it tries to procedurally recreate an American city pattern. We relied on the find shortest path Houdini node to create the arteries. And at last, the tool is calculating the best fitting grid pattern to match to the size defined by the user inputs. The tool can procedurally create an infinite solution of different cities. The next step is the city zoning. We have used this extra utility to define zones with specific attributes like a commercial or residential zone, but mainly to shape the cityscape. In a way, this becomes the vertical modeling tool of our city. We have used Houdini engine plugin inside Unreal to be able to design the city directly in engine, although the tool could also be used directly in Houdini for the rest of the procedural generation. This was a user-friendly way to model the cityscape, and we made a lot of back and forth with the art director and the cinematic department to shape it the way we wanted. Once we are done with the base city layout, the tool is outputting a big soup of metadata that would be used by downstream tools to produce the city. That would include a road network, the lots definition, and the sidewalk network. Among many other attributes we could also find in there, the road connectivity, the traffic density, or the pedestrian density. With this soup of metadata ready, we can now feed the city processor and start the final creation process. This dependency graph shows an overview of the key components of the city tools and their dependencies from top to bottom. This is important because in the procedural flow, it shows where we would need to regenerate the city in the case we were to change a role at a given point. The dependency graph is broken up into three stages: the city base, the city core, and the set dressing. And this is an overview of what the graph would look like inside Houdini, with all the actual visible dependencies. The first step in the creation of the city is to well define the roads and their geometries. In order to do that, we take the road network provided by the city layout tool. It is composed with spline made out of 2 points. It has a 3-layer road hierarchy that carries all the metadata it needs, like the road width, the road IDs, number of branches per intersection, etc. We then trim each road section by a carefully calculated amount based on the angle at which the road connects, and leave enough room for the intersections. Each road section would then be filled with the adequate number of road modules. For each width, we have 3 available modules, 20 meters, 10 meters, and 5 meters subsection. This way, the entire road geometry is mainly made out of 9 basic bricks. Because the sections can technically have any possible length, we keep some room for a little bit of scaling on the smallest 5-meter module. For the intersections, we are filling up the leftover room with road modules scaled to the appropriate length. We then set their pivot at the intersection center, while they aim outward toward the road sections. Once properly calculated and assembled, the road modules are replaced by their higher resolution counterpart. This represents the geometry as it would appear in Unreal. And the road processor would then output a point cloud that would be used to instance the module inside Unreal using our role processor pipeline. The road module would have 2 sets of UV, plus a relative vertex position stored as vertex colors for maximum control with the shading. It would feature some tapered skirt on the side to ensure smooth connection between them, and would also have a bit of curvature to add a bit of realism to the world. Once the road network and precise road footprint is established, we can move on to the extraction of the traffic information. Using the metadata of the roads, we would trace splines for each lanes and interconnect them to create the traffic base grid. We can briefly mention here that this network of splines contain all the information about the traffic and would later be imported to Unreal via a point cloud. It would then be interpreted by the traffic tools to be turned to a zone graph. Julien Marchand will cover more in detail this topic later in the presentation in the section Bringing Life to the City. Next in our city generation process would come the freeway generation. For the city's freeway, we knew that the chase sequence would happen at least in part on it. This had an influence on the organic and tentacular look of it. We were after an iconic landmark easily recognizable in the city, with complexity and pillars for the cool cinematic parallax effects. Around the needs of the cinematic department that were mostly focused around the big exchanger, we have built the rest of the freeway path. It is composed of 2 closed loops, 1 overhang passage, and 55 access ramps over 25 km of usable freeway. To iterate quickly, our designers needed a way to edit the freeway and find what would work best for the chase sequence. An Houdini asset was used in Unreal and would take an input curve to generate a simple freeway deck geometry, allowing designers to create a good path for the chase. There was a lot of back and forth between the designers and the procedural team to make sure the freeway's shape would serve the demo well, both in look and function. Once the shape of the freeway was locked in place, the designer's input curves were brought from Unreal to Houdini and embedded into the city graph, keeping the freeway generation as part of the main city process. Because of its organic nature, the deck had to be procedurally generated as a megamesh. This is one case in the city where we couldn't entirely rely on module instancing, and we had to create custom pieces that would fit a specific area. The megamesh would later be divided in smaller chunks of 100 meter size, so it can fit the open world streaming workflow and help Lumen for performances. All the other set dressing pieces, the barriers, pillars, signs, and debris, are nanite instances scattered along the freeway path. Finally, as for the road processing tool, the freeway tool would output several point clouds to be instanced over inside Unreal and would provide metadata to the rest of the graph. It would output several sets of meshes, including the freeway deck and its collision proxy. With the road and the freeway generated, we can now move on to the lots processing and the building volumes generation. For the lots, we start from the basic lots definition provided by the city layout tool. Remember that it also carried the height information defined by the cityscaping we had done earlier on. We first need to ensure that we won't rise buildings where the freeway is, so we remove it. After several layers of geometry cleaning and filtering, we are subdividing the lots. The subdivision is using an algorithm that ponders building height versus available surface. The more the surface, the larger the final footprint can be, but only if that is to support a tall building. Of course, we introduce a little bit of random in that process to not make it look totally linear. The lowest building height are automatically divided into New York-style lots with the typical staggered style subdivision. As the subdivision is done, you can notice in red all the lots that have been filtered as non-suitable for building, either by their shapes or their topology. This is where we have introduced a system to ensure we would cut down on producing arbitrary data and try to quantify the world a bit more, introducing the building DNA. Each building of the city would be described by a custom DNA. The DNA starts with the footprint. We have created 17 of those, and any building in the city would have one of this shape as a base, so we would always know what to expect. Once the footprint is established, we added few attributes to complete the DNA. The size in X and Y, its position and orientation in space, a height of extrusion divided into 3 layers, and as an extra bit of variation, mostly for taller structures, we also added the possibility for any building to be either cubified or with staggered floor like the Empire State Building. As the last strand of the DNA, we would assign a specific building style. With this technique, we could create an infinite variation of buildings, ensuring every single one of them would be unique. We can now replace non-suitable parcels with our collection of footprints and ensure they would fit the original space available. For the rest of the subdivision, we simply replace them with our available footprints. It works in 2 stages. First, we adjust how much percentage of a given footprint we would like to see in the city. We then ensure it would be compliant with its given building style. This is important because each building style has a limit on how it can be built. A minimum wall length under which the building generator will not be able to fit the module that composes it. More on this will be described in the procedural building topic later on the presentation by Robert Osborne. The final part is the creation of the building volumes themselves. Populating the rest of the needed DNA strands with some global controls, we would add a little bit of extra noise to adjust the overall feeling of it. We could finally choose how much of a cubified or a staggered building we would want to see. So before Robert covers the procedural building more in details, we will go over the rest of the city graph, and in our next step we will look at the creation of the ground. The ground would be under high scrutiny since it's where the player would spend most of its time. We needed here more than ever a very high fidelity in the asset and thus the needs to use instancing elegantly. This represents our collection of sidewalk and floor modules. We didn't have availability for displacement directly in engine, but that wasn't a problem. Since Nanite removed all triangle limit, we end up pre-displacing the floor tiles. Using modified Megascan surfaces with their displacement maps, each tile could count up to 500,000 triangles. This gives you a level of crispiness and fidelity that we could have never achieved otherwise. So now, as the city layout tool has provided us with a network of splines for the sidewalk and the lots definition, we could take those meshes and have the sidewalk processor within the city graph ingested to scatter our module collection adaptively. Dividing each sidewalk section in a similar fashion to the road modules, it would fit the correct number of tiles, solve the corners, and the ground coverage area. And here we can see how the sidewalk processor works at different sidewalk connection angles. It would calculate how many tiles needed to make the sidewalks, randomly assign types, and solve the external and internal corners independently. Notice how for the inside corner, the 2 triangles pieces scale non-uniformly back and forth to adapt. For the ground itself, we would subtract the building coverage to save a bit of surface, and then cover it with a point cloud where the density would be adjusted to its ground tile size. If you recall the 500,000 triangles pre-displaced piece shown before, here you can see how many times we would use it over the city ground. 2.5 million times, that is. Yeah, that is 1.25 trillion triangles for the ground itself. We wanted things to look sharp and good. And that shows the same point of view inside the engine, with on the right the different instances that compose the ground. A little close-up shows you the final result more in details. This is a good representation of what the procedural teamwork was on the Matrix Awakens experience, a giant puzzle solving with instances. Now that we have our ground covered, we can move on to the set dressing of it. First, we would harvest and filter all the areas that are left untouched, basically where there are no sidewalks or no buildings. We have defined 3 main leftover zone types to describe the city: the plaza type, the freeway type, and the parking type. To populate those areas, we would use our instance-packed blueprints workflow, also shortened biomes, Those are pre-assembled packages of assets, and this workflow is described more in depth in the presentation from Levi, Creating a World, that I invite you to watch. To distribute those biomes among the leftover areas, we have used the scattered technique using the UV space of the zone. With the UV layout node of Houdini, this is a very convenient way to let it scatter objects while ensuring that they would not overlap with each other. For the use of the city graph, we had developed our own version of this tool and called it the packing scatterer. It would take each dependent zone, measure its longest edge, and take it as orientation reference. It would then try to best fit the biomes together with the possibility to choose between different patterns and angles. We have used this tool literally all over the graph to procedurally populate areas in an organized fashion. That also includes some of the rooftop for the buildings. This shows you a fun example of what the packing scatterer can do to cover any type of area with organized pattern without any fear of overlapping instances. The last images are showing the result of playing with different options and inputs on the tool. And now we come to the road decals in the ground covering process. We are taking the traffic and parking lanes calculated after the roads and parse them with points for the different types of decals. Over each calculated points, we would spawn a simple plane that would feature a decal material. Each marking that you see here is an instance plane that is carefully placed at the exact ground level. It has a decal material with opacity for finer details. The wireframe view gives a better idea of what's behind the scene. If you remember, during my description of the road processor, I mentioned that the road isn't flat. That actually proved itself to be a bit of a challenge. For bigger chunks like the crosswalks or the tire marks, the plane would need more subdivision to adapt to the road topology. This is why we have used here a different approach. The curvature of the road makes it a totally arbitrary object, and this was one of the cases where we had to use a mega mesh. So here, the bigger planes were projected on the road geometry to match its topology, and then assembled to a bigger mesh. Another interesting challenge with the decals were the solving of complex intersections. A procedural graph would analyze and interpret the lane system to create believable markings, draw rows, and basically add life to it. So now that we have produced a full procedural city, we have control over every single bit of information. So we can easily extract it and provide it to the audio department so they can work their magic. To provide this data, we would cover the final city result surface with a 3 meters density point cloud on which we will store the metadata. And by using a proxy geometry of the city, we would use its own ambient occlusion and indicate to the audio team at any given point the amount of reverb it can expect. Or tell them what type of sound it should produce. So that now we had a good overview of the city generation process, let's have a glimpse of what the Houdini graph is actually like. This isn't all of it, but it gives you an idea. This graph would take about 25 minutes to produce a totally new 4x5 km city with its 8 million instances, meaning that in 25 minutes, you could have a new city solution entirely different from the previous one. As a final look at the city generator tool, this is an accelerated demonstration of all what we have covered in this presentation. This is a 1-minute speedrun for a small city example that demonstrates how you can generate a world all the way to have it as a playable experience in Unreal. It shows how the generator enables you to produce a new city from the very first curve input to the road network tweaking, the vertical shaping, fine-tuning of its building, to its final generation with the rule processor. In this last part, you can actually see the rule processor in action for the generation in Unreal, although this topic is covered more in detail in the presentation by Levi, Creating a World. You can actually try it now by yourself, as we are providing you with Houdini files and basic Unreal templates to play with. So, some fun statistics to look at, and among those one that is very interesting to mention and that represents well how the city processor would work. Over the course of the project, we have regenerated the city 53 times. For every generation, we would scout the city and look for what we can improve in the procedural rules, fix bugs, add details to it, and finally regenerate the city, at least in parts or sometimes globally. That process, including the import in Unreal with the rule processor workflow, was possible in a couple of hours for the final version. Meaning that technically we could have had an entirely new city to discover several times a day if we were to change it. Let me now introduce Robert Osborne that will present more in detail the process behind the building generation.
I'm Robert Osborne, a senior technical artist at Epic Games. I'm going to talk about the building generation in the Matrix Awakens demo. Let's talk about the procedural building generation in the Matrix Awakens demo. In the prototyping phase, we wanted to keep workflows as simple as possible, one DCC straight into the Unreal Engine. Houdini and Houdini Engine are obvious choices for prototyping procedural ideas and workflows. Iteration speed is king when you want to evaluate concepts. We did a lot of prototyping and iterating. A great example of this ethos is the building module template generator, quickly allowing building module proxies to be created on demand to specific sizes. A building shape grammar system was needed to make the building generation as agnostic as possible, avoiding hard-coded behaviors that would constantly need to be reworked and debugged. This is what I started with. Wow. Looking back, I'm having a hard time understanding it myself. Luckily, we were still prototyping and iterated on the shape grammar look and feel. Here, the building generator is being used in Unreal to add an extra building to the small city level. Let's reposition the building to fit on the pier properly and change its dimensions. Now I'm changing the prop placement density and seed. Let's lower the height of the building. Finally, I'm changing the style of the building and making it wider. There, done. Building added. As we entered production, we had a good idea of how the city graph data would drive the building generation. JSON was chosen as the format for the building definition files during prototyping. An automated BDF pipeline was implemented in time for production, giving human-readable data that could be edited quickly to validate and debug with. The data fed to the building generator consisted of volumes with a BDF tag assigned per primitive face. Here, each color on the volumes represents a different building style. Here we can see how the data flows inside the building generator in order of operation till final output. Output was in the form of point clouds and roof geometry passed into the city graph or directly into the Unreal Engine using Houdini Engine. Input volumes were cleaned carefully to give the best chance for cleanly sliced floor primitives to be generated in a consistent and ordered manner. The assigned building definition file tag allows the floor intervals to be calculated from the BDF's level dictionary, and the volume is sliced accordingly. Once we have the floor slices, corner types are calculated using the dot product between the primitives and walking around the floor primitive IDs in ascending order. Split corners are recognized using a collinear tolerance to distinguish if adjacent floor primitives should be considered in line. Corner caps, when defined in the BDF, are prioritized over a split corner type. We wanted a flexible shape grammar syntax for defining the module placement behaviors on building facades, allowing for rapid end-user iteration without having to publish updates to the building generator. This is a typical shape grammar. The vertical bars represent a module bucket used to define module placement behaviors. The alphabet characters represent a dictionary key to look up the module metadata like width and height. Circular brackets are used to define an infinitely repeatable macro pattern of modules. Square brackets are used to define a fixed repeat of macro pattern modules. The asterisk character specifies that all modules in a bucket can be scaled to fit the shape grammar to the length of the facade. Selecting the most appropriate grammar for a facade is driven by the total length of one full iteration of the shape grammar. The shape grammar with the smallest fit gap, not greater or equal to the facade length, is selected. Here we can see how different grammars are used as the length of the facade increases. With the most suitable shape grammar selected, the modules are placed on the facade. Here we see the module placement and scaling according to the grammar being used as the facade length increases. Buildings are generated independently of neighboring buildings in each building lot. This gives better parallelization for the graph execution. Occluded modules on connected building walls need to be removed for memory and generation performance. In the city graph, each lot of buildings are passed in as one job. We take the full lot of buildings minus the building having its modules occluded and merge and clean them. The building being occluded is booleaned against the rest of the lot, creating a Boolean shell that represents touching wall heights. Additional sample points for each module derived from the module bounds are added for performing intersection testing. These sample points and the module pivot point are raycast against the intersection shell. Only modules where all sample points are deemed to be touching the intersection shell are flagged for removal. As corners wrap around facades, extra sample points are added for corners. The occlusion has to be conservative, as re-adding modules to cover holes is complicated when you consider primitive data for windows and props. Even with this conservatism, a 25% reduction in building modules, props, and decals is achieved. The conservative approach is shown by the columns of corners still present inside some of the building shells. We needed to indicate to the CityGraph's sidewalk furniture placement system where building entrances existed. The place modules on buildings carried tags to define functionality, such as corner, wall, entrance, etc. These tags allowed the building generator to provide volumetric data to simulate exclusion of street furniture in front of building entrances. Once in production, new feature requests were added to the building generator, one being multiple BDF support on a single building volume, others being window treatments and window signage. It highlighted the need to have a production version and a development version of the building generator, while new features could be iterated on in a development version without blocking the CityGraph or end users using the production version. Building prop brandings were assigned per facade across the city, with just a simple modulo seeding using the lot ID and building ID for determinism. Being able to have the building generator run directly in Unreal using Houdini engine allowed end users to play with prop densities and adjust seeding. Controls were exposed on the UI for this purpose, allowing prop meta to be tuned and then exported into BDFs. Here we have the building generator running in the Unreal Engine via Houdini engine. On this building, I want to place fire escapes on it interactively using the volume overrides functionality. The volumes are given their override functionality by adding actor tag strings. For example, the word fire escape is used for placing fire escapes. The override volumes are passed to the building generator using the exposed tag volumes input. Let's change the prop branding and extend the red coffee shop props to continue into the recessed courtyard area. Again, using a volume with an actor tag to represent the desired branding on the props. For the window cube map primitive data, we wanted to create believable functional rooms. We built a connectivity array along each facade of modules that have a window tag. With this, we can determine the maximum size of a room that can be placed. After placing a room, all instances in the room get a room ID, and we move to the next window module without an assigned room. This continues till the facade is full of assigned rooms. A Vex dictionary holds several seeding arrays to select rooms based on the building function. In the movie, you can see lights being switched on per floor ID, then by room ID on each floor, and finally by room size. For window treatments, window helper objects were added to level 1 modules to define the surfaces of the windows if present on a module. This data was stored in the prop anchor points for each module using the helper category. We needed a subsystem to populate window signage. We knew where each building entrance was and only placed signage close to entrances using the window helpers. The window signage data is exported in a building definition file for use with the window composite system. Composite layouts were selected by the assigned facade branding. The prop placement vex code with different filtering was used to place the composite layouts in place of a normal window frosting instance, which would be removed during the signage pass. An internal vex dictionary was used to encapsulate placement rules, brand groupings, and functionality with certain masking used for building styles. All the roof geometry was derived from the input building volumes. Building a one-stop recreate all roof geometry from the floor slice primitives was too complicated, and edge cases popped up with every tweak. UV generation and scaling controls were added to deal with unique roofs which could not be instantiated. The UV controls were exposed on the building generator UI for end users to evaluate good default values. Building volumes developed from simple cubes to complex cubified volumes. Split roof support was added to deal with the complex volumes as best as possible. Not all building modules were created equal, the biggest issue being some modules got sliced at the lower window edge, which is recessed back from the common facade plane. We had to create a function to analyze the floor slices at split roof edges and apply a push or pull inset to hide these gaps. The building generator needed to be scalable due to the sheer amount of data it was generating. Almost 7,000 buildings with props, module occlusion, window treatments, window cube maps, ground decals, and roof geometry. This all generates in 13 minutes using PDG on a single X3990 Threadripper PC. Some data sets from the large city generation. As we entered the end phase of the project, the building generator graph looked like this. The volume curator pass just before the building generator allowed the generation of override volumes to place fire escapes. A masking scheme was used to populate fire escapes only on certain building groups and styles. It also allowed directed prop placement via primitive groups. Example, no props were placed in the Brooklyn-style courtyards. Multi-BDF volumes were given steps to hide transitions of the building styles. Multi-BDF style combinations were also tweaked following art direction concerns. The volume curator also allowed for optimizations late in the project. Memory was a concern, so the global height of the cityscape was reduced in certain height ranges, allowing a surgical strike without potentially causing a butterfly effect had this change been further upstream in the city graph. The volume curator was also used to target specific problematic building volumes and associated metadata. So, while not directly involved in the building generator, I wanted to mention a workflow we started using for referencing viewpoints in the city. As the city density grew, the ability to communicate points of interest in the city with accuracy became all too apparent. We started to use the Unreal Editor command line Bugit to snapshot points of interest for quick sharing, tagging in channels with a screenshot and a Bugit Go string, till we reached the pinnacle and Jiras contained Bugit Go information. With all these data points for POIs starting to mass, the Bugit Go HDA happened one afternoon, allowing reference points to be available in Houdini datasets to observe behaviors and debug with. Pasting a Bugit Go string into the Bugit Go HDA will generate an indicator in Houdini Worldspace. We have a reference in Houdini Worldspace that can be jumped to quickly using frame selected. This easily allows associated input metadata to be explored, debugged, and edge cases solved. You can round-trip this data, passing a Bugit Go location that is derived from the currently active Houdini 3D scene view back to the clipboard. Pasting the clipboard back into the Unreal Editor command line gives a super quick back and forth for cataloging and exploring the city dataset. For bugs, this is especially efficient to get the location of an edge case generation, to examine the metadata and step through your graph and debug with. Allowing the problem buildings to be isolated in the Houdini scene, iterate on the fix, test locally, and publish the fix. Super useful for smoke testing known results after an update to the building generator. With the sheer number of building volumes, we were struggling to identify issues in the vast sprawling city we were building. We literally could not see the buildings for the city in some situations. While we had Bugit and Bugit Go to teleport around the city and investigate issues, we really needed a structured way to sign off on all the building styles and building features without the distraction of the beautiful city. A volume filter HDA was created to give targeted collections of volumes to feed into the building generator. Houdini is great. Chain your meta filtering into generation, then add some automated output. Now you are slicing and dicing the data to create sets of maps in the editor to systemically close the project. Not carrying the full weight of the city during smoke testing increased the iteration speed greatly. Special thanks to some of the quality people I was lucky enough to work with on this project. And now let's talk about wave function collapse. Wave function collapse is a term from quantum mechanics in which a wave function in superposition collapses to a single eigenstate. This concept has been applied to game development in the form of a constraint satisfaction algorithm. It can have many applications including texture and model synthesis, map generation, and gameplay. In a constraint satisfaction problem, a constraint is a rule that the system must satisfy when solving. Here we have a cat in a 2-tile grid constructed from 2 options, the tail and the head. There are 2 constraints here. The head can be to the right of the tail can be to the left of the head. it is simpler to always consider these constraints in pairs. Here we increased the grid to 4 tiles and added a third option, the body. We can see a total of 6 constraints. Next, we introduce a special option, the empty option. Empty options are useful when you want to ensure that the bounds of the grid will not form open-ended solves, like having a body option at either end of the grid. Empty options can be adjacent to each other. If you have an A to empty pair and an empty to B pair, then an A to B pair can be made. Let's see what it looks like to collapse a 1D grid. We initialize a 6-tile grid where each tile represents all of the options allowed. The number above represents the remaining number of options for a given tile. Let's make an assumption that the tiles are surrounded by hidden empty options, and both ends of the grid must be modified to only allow options that can be adjacent to an empty option. You can see that the number of remaining options has dropped from 4 to 2. This number will also represent the value of entropy for a given tile. We now begin a recursive cycle of observing and propagating. In the observation phase, a random minimum entropy tile is selected. A selection is randomly made from the remaining options. The tail option was chosen and the remaining options on the tile has dropped to 1. In the propagation phase, all the tiles adjacent to the observed tile must adjust their domain to satisfy the constraints. The propagation continues recursively until no more tiles are modified. With every iteration, more tiles are collapsed down to a single option. The solve keeps iterating. Finally, the solve reaches a state where the grid contains only collapsed tiles. Here we can see this process in 2 dimensions using a 6x6 grid. Here we see the process in 3 dimensions using a 3x3x3 grid. A wave function collapse model is a data asset that stores constraints. A constraint is stored in the form of a key option, an adjacency, and the adjacent option. Defining constraints can be difficult. Some implementations have used label-based systems, but that can be confusing or complicated from an artist's perspective. Our implementation derives constraints from arbitrary layouts. By doing so, wave function collapse models can be built visually, and it may help in discovering new options that are required. You can simply specify a resolution of a grid to solve. There is also an option to use a grid actor, which is a blueprint that visually shows the bounding box of the grid. One advantage with the grid actor is that it can derive starter options based on static mesh actors that sit within the grid. On the left, you can see a few tiles pre-placed inside the grid actor and the 2 different outputs on the right. It is a great way to combine art direction with proceduralism. The city had so much complexity at street level, but once you went into drone mode, it became obvious that more complexity was needed from the bird's eye view. In total, there were over 2,600 unique rooftop structures made. The wave function collapse model contained just over 5,000 constraints. All of this with only 33 tileable meshes. Solving these structures one by one was not scalable, so we created a solution that can derive grids from point cloud data. We created editor utility widgets that can do some post-solve processing. Here we are swapping wall materials, roof materials, and per actor custom primitive data to create color variation. We can derive a grid from a solved actor and allow for arbitrary logic based around tile neighbor rules. In this case, we use neighbor rules to place props on walls. To reuse existing Houdini methods made for scattering props, we made a method for exporting roof-only surfaces. Roof prop scattering was done in Houdini and reassembled in Unreal Engine using point cloud data. And here are some wave function collapse results in the city. The wave function collapse plugin was created by Joji Tsuruga, a senior technical artist on the special project team. It will be available as an experimental plugin in Unreal Engine 5, and we are excited to see what the Unreal Engine community will create with it. And now, here is Julien.
Hi, my name is Julien Marchand, and I am an engineering director at Epic Games. Thanks for joining me today and see how the crowd and traffic teams, empowered by the Unreal Engine new AI technologies, brought life to the city for the Matrix Awakens demo.
Having procedurally generated the static content of the city, the remaining challenge was to immerse the player by making the city truly feel alive. To us, it meant two things. We could not compromise on the density, and we had to ground the persistencies of these elements inside the world. Filling the world with a vast amount of interactable, autonomous agents became obvious, and in this case, the crowd and the traffic system became the natural choice for a city. To meet those requirements, we had to leverage a new technology called Mass AI. Before moving on, let's take a step back and have an overview of the Mass framework, a data-oriented design for Unreal Engine, of which Mass AI is a specific use case. The Mass framework comes in three separated plugins: Mass Entity, Mass Gameplay, and Mass AI, which have a feature set built on top of the previous one. These are all coming experimental for the Unreal Engine 5.0 release. Let's start with Mass Entity, which holds the data-oriented framework fundamentals. To better understand it, let's compare it with a classic object-oriented model, in this case, the actor component model for Unreal Engine. This model allows for a very flexible way of composing the logic of the entities, in this case, actors that we want to bring into the world. This model has been a staple for video games development for many years. However, the flexibility of this model leads to code and data incoherency due to them being updated sequentially. Also, the way the actors are composed does not guarantee that their components are aligned in memory. Their access is almost guaranteed to lead to cache misses, which are expensive for the CPU. Moreover, components can sometimes become bloated and part of them may not be required for a particular actor. On the other hand, the Mass framework for Unreal Engine proposes an alternative way of storing our data and decouples it from the processing logic. We have fragments that are very small data structures and entities which simply hold pointers to the fragments that represent them in memory. The fragments of entities of similar composition are stored contiguously in memory. And finally, entities do not hold pointers to any data, so in this case any fragment, that it does not care about. As mentioned, we decorrelate all processing logic from the data composition itself, which is all within the fragments. To understand on which entities we want to execute some logic, we make use of an entity query. The entity queries filters the entities, which holds pointers to the fragment required for a particular logic. Processors are where the batch update will occur and where the logic will run. For example, we could be updating the position fragment of all entities at once by reading from their velocity fragments, but that can only occur if an entity has both of these fragments. This segregation is what enforces data encode coherency, minimizes cache misses, and will trivialize concurrent execution in the future. These are the fundamentals that are pushing the limits on the numbers of entities we can simulate at once. The mass gameplay part of the framework is what allows us to tangibly bring mass entities inside the game world. This is where we'll find our mechanisms for spawning, visualizing, LODing, etc. Namely, the entry point to bring mass entities inside the world is the mass spawner, which is a regular actor that you can place in your level. Looking at the properties for the mass spawners, the only two things you should really care about are what to spawn and where to spawn these entities. We will be answering these questions in a moment. Our purpose was to bring autonomous agent inside the world, and this is where the Mass AI plugin comes into play, which encapsulates features for navigating the world, animation, behavior, etc. But more importantly, let's remember that what we wanted was to bring life to a city, so we were not shooting for just any AI. What we ultimately wanted was a crowd and a traffic system. And the way we built these plugins is exactly how we envision developers to leverage and extend on the Mass framework in the future. These plugins hold all behaviors that are specific to these use cases. Before getting into the specific of the crowd and the traffic behaviors, let's link back to the procedural data that we leverage to answer one of the two aforementioned mass spawner questions: where to spawn the entities. The answer to this question was the zone graph, which is another experimental feature coming with the Unreal Engine 5.0 release. The zone graph is a lightweight design-driven flow for AI, which for the context of the Matrix Awakens demo, replace our need for an AI nav mesh. It is an ecosystem of point-by-point corridor structure connected by intersections. It also stored actionable tags that can be either static, such as identifying a pedestrian from a traffic lane, or dynamic, such as an open or a closed lane, that will later be useful to dictate our AI behaviors. In fact, we leveraged the zone graph to have a density-based distribution of entities for both crowd and the traffic, whereas for the parked vehicles, we were more interested in a static point cloud distribution. The mass spawners support both of these options, along with many others when it comes to deciding how to distribute mass entities inside the world. For the crowd, we merged the procedural data representing the pedestrian density, along with the pedestrian lane network, to create a network of interconnected and properly annotated zone graph for the crowd. Although hard to see, the annotations denote what they are for, whether they are crosswalk, sidewalk, or intersection lane. They also hold information about the expected density and whether they are currently closed, as you can see in red, or not. These are the lanes upon which we generated spawn location at varying distance based on the desired density. For the traffic, we did the same thing. We merged the procedural data representing the traffic density, along with the traffic lane network, to create a traffic zone graph network, and then generated the spawning location for the various vehicles. Note that for the traffic, we had to do that operation for both the city lanes and the freeway lanes, and then interconnect both networks. Finally, for the parked cars, we simply directly spawn one at every location fed by the point cloud. And voila! Having distributed our entities across the map, we now need to answer the other mass spawner question, which is what to spawn. We are talking more than just visuals here. We need to be able to define how these entities will behave across the city. A mass entity definition is a new asset type that we use to easily dress the list of fragments that our different entity use. Amongst the important aspects of the definition are of course the visual, where we want to show at which LOD, for example. The LOD parameters themselves are defined there. What are the cutoff distances? What are the visibility angles we care about? And what is the maximum budget per LOD? These two mechanisms work out of the box with the mass framework and are paramount to supporting an extra large number of entities. This is also where we added all necessary fragments required by the relevant processors to simulate the mass entity's behavior. And for that, we took slightly different approaches for the crowd and for the traffic. For the crowd, we made use of a state tree, which is another new technology coming experimental with the Unreal Engine 5.0 release. It serves as a scalable and general-purpose state machine with an intuitive and compact UI presented by a decision tree structure. The entire crowd behavior can be seen on screen, and it describes all the states that a crowd member could be in, whether it be wandering, idling, fleeing, etc. The state is selected by running a top-down evaluation of the entry conditions and run its associated parameterized task. Once completed, the tree will route to its default transition state unless a different transition condition is met before. Another benefit of the state tree is that it is tightly packed in memory, which blends well with the mass framework. In this capture, we see the various crowd behaviors at play, such as walking around, waiting at intersection, but we also made the characters believable. The animation coverage proposes various walk style and speed, smooth start and stop animation, and also manages a head look at along with the upper body orientation independent from the character current velocity. We also note that it reacts to its surrounding, be it the player or the other crowd members. Specifically, we develop a new force-based avoidance that handles both dynamic and static obstacles at high performance. The crowd members can also respond to physical collision, such as playing a one-off animation before resuming their behaviors. We use the animation state machine to run on the closest crowd members in sight, but all the data it used came from the mass animation processors that was feeding the relevant data from the entities fragment. As mentioned previously, the mass LOD system is key to handling a vast amount of entities, in this case, our 35,000 crowd members. By default, the framework handles 4 different LODs, along with a significant float point value between those levels. On the screen, we can see in red 10i LOD, which are full-fledged meta-human actors with facial animation. In yellow, 20 medium LOD, also full-fledged meta-human actors with lesser facial animation. In green, up to 500 low LOD, which are lightweight vertex animated meshes. The rest are not visualized. If you're interested in knowing more about how the crowd meta-human were made and how we animated the instant static meshes, I encourage you to listen to the Curator Tech Talk. Because of the mass framework, we also attained a great level of persistency. No matter the LOD we were switching at or from, it allowed us to always retain the current behavior evaluation, persist the visual, so that if you go far and back, you can find that cool looking character again. And finally, allowed for smooth animation transition, even from switching from a vertex animated mesh to a full-fledged actor, since the runtime animation data was persisted in the animation fragments. For the traffic, rather than using a state tree, the behavior were all programmatically made in mass processor, which is to say that the framework does not constrain you to an approach over the other. The most typical behaviors were the follow on lane and wait at the intersection. To prevent vehicles bumping in each other, we relied on a queuing of vehicles along a lane. A vehicle would know the distance to the next vehicles to manage the speed at which it goes. When a vehicle intersection lane closes, upstream vehicles will speed down and stop at the end of the lane. Not unlike the avoidance for the crowd, the traffic vehicles also had to manage obstacles, such as the player standing in the way or when creating car crashes. These obstacles could supersede the next vehicle for determining the speed to go at if the obstacle distance was shorter. In the absence of the player, we assumed the simulation to run orderly. To switch it up and to allow the traffic to circulate everlastingly, we had to support lane changes and lane merges. This occurred when an empty spot was detected on a neighbor lane. We would create a ghost entity to simulate the future presence of the vehicle on that lane. Once the transition was complete, we would then remove the vehicle reference from the previous lane. This was particularly useful for getting in and off the freeway. Similarly to the crowd, the vehicle had their own LOD parameters. There are a total of 17,000 traffic vehicles and 38,000 parked but drivable vehicles. On the screen we can see in red 10 ILOD, fully simulated physics vehicle actor that can be deformed, destroyed, and interacted with. In yellow, up to 150 medium LOD that are still running physics but with simpler suspension and all simulated within the mass framework. In green, up to 5,000 low LOD, which are instant static meshes following simple curves and following position updates. The rest are not visualized. For the traffic actor spawning, since it could happen at a moment's notice, we made use of actor pooling to alleviate the cost. Also, note that the parked vehicles are not just there to be pretty. The player can hop in any one of them, drive around, abandon them, and get back to them later on. Finally, the last step was to make the crowd and traffic system work together, and that's where the intersection coordinators came into play. This processor was in charge of managing the phase for which lanes to open at which time, when was it okay for the pedestrian to cross, when could we allow vehicle turning and when we couldn't. We had a high number of intersection configuration which added to the complexity. Lastly, to manage the flow density for both the crowd and the traffic, this is where decisions about where to go next were made, as to prevent the downtown populace to invade the lowtown, for example. In the end, it was not always perfect. We were not city engineered by any means, and that is why we had to iterate on the city and density a lot. We thought that combining a super high density with a persisted simulation and adding a stoplight at the end of a freeway was a good idea, but it did create some nice anecdotes. To conclude, to bring life to any world, it is true that having a high density is a great foundation, and the mass framework helped achieve that easily. Even if there exist tricks to fake it, who is to say? Perhaps nothing exists outside of the current view you are seeing. However, if density is great, persistency is king. It really helps immerse the player inside the world, and we hope that this cut will speak for itself. You can note the green moving square to be the traffic vehicles, the blue one to be the parked vehicles, and the little white ones are the crowd members on the sidewalk. This is the result we ended up with, starting small, leveraging the generated procedural data, all the way to simulating upwards of 100,000 mass entities at once through the crowd and the traffic system. This is how we brought life to the city, and it is a result we are very proud of. Thank you for listening.